Welcome to Functional Fundamentals in SwiftUI. I hope to answer some of your questions about why do we need to learn this stuff. In this session, we'll look at some of the long-standing advice about coding safely in Swift, what it means to be Swifty. Along the way, we'll underscore some of the lessons from functional programming, and we'll look at the direction we're heading with Combine and SwiftUI. And of course, for fun, we'll play with some code examples. Given the times, this is not one of those deep, blow-your-mind functional programming talks. In fact, it's pretty basic. When we're all feeling stronger and better and able to think more clearly, we'll gather again for a talk about functors and monads. Over these past several years since Swift was introduced, we've still been using Objective-C under the covers. We've been using it for UIKit and AppKit and anytime we have to write anything useful for our apps. But along the way, there have been changes in the way that we write Swift. Last year, with the introduction of SwiftUI and Combine, we could begin to see the future and see that we'll actually be writing things in a more Swifty way and not having to make these accommodations for Objective-C. In fact, coming soon with WWDC, we expect to see more changes in the way we write Swift, as we find more changes in SwiftUI and even more changes in Combine. Let's start with what we'll call an impressive demo. Here's your basic one button, one label application. We'll write it 2 times. We'll write it in UIKit and then we'll write it in SwiftUI and look at some of the differences. When we tap the Tap Here button, we notice 3 changes. The text of the label changes from Hello to Hello World. The color changes from gray to green. And the Tap Here button is disabled. In UIKit, it's your standard MVC. We don't have much of a model, so we have 2 view objects. We have our UI label and our UI button, and we have our UI view controller mediating. The UI view controller has an outlet to the UI label, and it has an action for the UI button. As for the UI button, it's linked with a target and an action to the UI view controller. Its target is the UI view controller, and its action is the greet method. When we tap the button, the greet method is fired. In turn, it talks to the label through its outlet. It changes the label's text to Hello World, and it changes the color to green. In addition, the action knows who the button is. It knows who the sender is, so it's able to send a message back to the button to disable itself. And that's our UIKit version of this simple application. The UI button knows its target and its action, and that's all it needs to know. The target is this object and the action is a selector. Here's our UI view controller code. The view controller has the label and the button. The greet action is labeled @obc so that it is visible once we set it using the add target action. And inside you can see that greet talks to the label and the button. Here's how we attach the button to the view controller's action. We send a message to the button, add target, and set ourselves, the view controller, as the target of the action. We specify the action by providing the selector the name of the method, and the name of the method is greet. And as is usually the case, we specify that this should be fired when we touch up inside the button. Again, the action is specified with the selector, the way of identifying that method. And because the method is @obc, we're able to pass it into the add target method. So there's our UIKit version of the button specifying the target and the action from the view controller. Things change quite a bit in SwiftUI. You hear a lot of people talk about the declarative nature, but there's a lot more that's different, and it's finally the payoff to having something that is more Swift-friendly in the way we write our GUI. We don't have a view controller in SwiftUI. We have this sort of parent content view. It's not a parent as in a class that contains subclasses. It's more of a container for the other view elements. And so our content view contains or instantiates the label and the button. And in SwiftUI, a label is called a text. The action is a method inside of content view, and the state is held outside of content view. We'll talk a little bit about that later. So when the action is fired, it sends a message to the state, and it updates the various things like the text color, and whether or not the button is enabled. So the trick in SwiftUI is we don't pass a handle to the action to the button. We actually pass the function itself. So now the button holds the method that it's going to call. It has a property named action, and we've passed it this function that takes nothing and returns nothing. And it is still attached to the state that sits outside of content view. So when we tap the button and fire the action, the state updates And in response to the state updating, our text changes its text to Hello World and the color to green, and our button is disabled. And so these are the two different worlds, the two different buttons. On the left, you see UIKit, where we set our button using the target and the action. And on the right, you see SwiftUI, where we set our action by actually passing that function over. This is functional programming. If you look at the code, here's what the label looks like. The label is just a struct. It holds a string that's going to be what it displays in there. Initially, it's hello, and then it changes to hello world. This is the string that's going to be displayed in the label. And so in the content view, when it's time to set that value, we have these state variables for text, is disabled, and color, and they're set to these default values of hello, false, and secondary color. We set up what our app looks like in the body of our content view. I've highlighted the things that we care about, and so we're going to ignore the spacers and the setting the fonts and the various things that affect the GUI, and we'll just focus on the label and the button. Remember, the label expects to be told what text it will be displaying, and because it's a struct, it's as if we have this implicit, this default created init here, which allows us to specify the text. So we're going to use this implicitly defined init when we create my label. And so here's our instance of my label that specifies its text is our state text, which is hello. And so when it's created, it first gets displayed saying hello. Similarly, my button needs to know the text it displays. It displays tap here, and it also needs to know what it does when you actually tap the button. What is the behavior of the button? And so we'll save that in a property which we call action. Now, this is not a small thing. This is huge. We're storing a function inside of a property. And we're doing it as simply as when we stored a string inside of a property. So this is our first step of realizing the whole goal of functional programming is that functions aren't special. The same thing I can do with strings, I can do with functions. And so here I have a function that takes nothing and returns nothing, and we're storing it inside of the property named action. So we have to define our function somewhere. We'll define it as a method in an extension of content view. And inside this action, we'll do three things. We'll set disabled to true, we'll change the text, and we'll change the text color. Now I say that, but actually we're just changing three properties. We don't know how they're going to be used. We're changing a Boolean named isDisabled, we're changing a string named text, and we're changing a color named color. You might worry that they're vars, but we've made them private so no one else can talk to them, and so only we can talk to it. And so in our private function action, we're talking to the private variables text, isDisabled, and color. And now we instantiate my button, and we instantiate my button by specifying what the text is and what the action is. Check this out. The text is tap here, and the action is this function. We're passing the function this time. This is also huge. We are passing a function as a parameter just as easily as we're passing the string tap here. So again, looking side by side, in UIKit, our UI button, we specified the target and the action, which was a selector. And in our button in SwiftUI, we're passing an actual function and storing it as action. So what about these state things that we see, these property wrappers that we see in SwiftUI? We're behaving properly in many ways. We're following the advice that we've tried to follow in Swift since the beginning. My label is a struct. Its property is a let, not a var. My button is a struct. Its two properties are let's, not a var. String is a value type. A function is a reference type. And finally, content view is also a struct. Because something has to change in an app or we don't see any point of having an app, these have to be vars, not lets. These are all vars. Remember, we've guarded from anybody else changing them by making them private. But how do we change them? We would have to make them mutating or go through some sort of a rigmarole to make sure that we can change the value of a value type inside of a struct. Instead, Apple has given us this new @state property wrapper. So let's look at our guidelines so far. Generally, we are doing structs, not classes. We're favoring value types over reference types. For the most part, we're favoring let over var. And in those cases where we do use var, we're limiting access by making them private. And now we have this state property wrapper that we're using to decorate our three vars. So we saw what View Controller had in terms of its pointer to the label and its pointer to the button. For our content view, let's just focus on the text. The other two properties are analogous. In the old days, we would have stored our text inside as hello, and we would have tried to change it from our action, and this wouldn't compile. We would have gotten the message that self is immutable, and so we couldn't change it. And the problem is that text is a string, which is a value type, and content view is a struct, and we're trying to modify a value type within a struct. One of the nice little workarounds in SwiftUI is this new state property wrapper, and what the state property wrapper does is it takes text and it stores it somewhere else, and it transforms text inside of content view to be a reference type. It is pointing to the value type that is now stored outside of content view. So even though we access it just like it's a reference type, it is still a string, it's still a value type. And now when we fire the action sends a message to text. Text has got a reference to where that text actually lives, and it's able to modify it. And so we can change the text from hello to hello world. And that's what state does. It allows us to store our values outside of our struct. And so this helps us continue to favor value types over reference types and favor lets over vars and limit our access and visibility of vars. But now we use state to use private value types as if it were a reference type. Along the way, we've seen a couple neat things about functions. We've seen that we can store functions as properties. And then in the init, we saw that we can pass functions as parameters to set their values as those properties. And that combined to tell us that functions aren't that special. Although we haven't seen it and we won't see it today, you can also return functions from functions. These two together combine to give us what are called higher order functions. A higher order function is a function that accepts another function as a parameter, or it returns another function. And then there's this last little guideline, which we really can't enforce in any way, but we really try to follow, and that is avoid side effects. In fact, that's what we mean when we say we prefer pure functions. So let's look at some examples of pure functions and examples that aren't pure. Here's an example called what time is it? What time is it prints the date. But this is about as non-pure a function as we can have. Each time we call it, we get a different value because the date has changed. We've got this external dependency on what the date is when we call it. That would make testing it really difficult. In addition, we're printing the result. So we're not even taking a result in and returning the result, we're printing it. So we're using this external print to the console also within this function. So we've got impurities on what we use and how we return the result. Contrast with this function, sum of one int and another int. In this case, we're going to just return the sum of two ints, int1 and int2. Int1 is passed to us as one of the parameters, int2 is passed to us as the other parameter, and the sum is what we're returning. So this is a great example of a pure function. When I call sum of 3 and 5, I get 8. Every time I call sum of 3 and 5, I get the same result. The idea is this is a function that only depends on its inputs, process those inputs into something that it returns as its return value, as its output. So this is a pure function with no side effects. There's nothing in the environment that can change how it behaves each time, like the date. And each time we put in the same inputs, we get the same outputs out. Here's another example. Let's say I have an enum for hand position in the game rock, paper, scissors with those three cases. And I have this function hand position that switches on the ints 0, 1, and 2. And so I've got a function that takes an int and returns an optional hand position. It switches on int and it decides is it a rock, paper, scissors, or none of the above. And so we look at the int that is passed into us, the 0, 1, or 2, or something else, and we process it and return rock, paper, scissors, or nil. That's our returned optional hand position. This is a pure function. There are absolutely no side effects. This depends only on what I pass to it, and it returns the results to us immediately. So when I call, for example, hand position from 1, I get the case paper, and I return the optional with value paper. Let's look at some non-pure functions again. For example, if I've got this variable that's multiplier and it equals 3, and I've got this function called multiply. Multiply takes an int and it returns an int. That's looking pretty good. It takes something, it returns something. But notice what it does. It takes that int that we pass in, that's good, and it uses the multiplier that is external to this function. And because it uses this multiplier, this is not a pure function. Similarly, I can define an external variable called result, and here's a function called increase. And increase takes an int and a delta, how much you're going to increase that int by, and it doesn't return anything. And so in its body, it sets the result equal to int plus delta. Int and delta are great. Those are parameters. That's what we pass in. The side effect is because we're not returning result, we're setting the value of this external variable to be that sum. And so this is not pure. We've used result. There's side effects that you can use to calculate and side effects that you're setting outside of your function as a result of running the function. And so when we increase 10 by 5, the only way we can see the result of this calculation is by looking at result itself and see that result has changed to 15. And you might think, one of the code smells is if you have a function that doesn't take anything and doesn't return anything, well, that immediately might tell us that we've got a side effect involved somehow. If we're not taking anything, we must be using something outside of the function. If we're not returning anything, we must be setting something outside of the function. Although that's a good rule of thumb, here's an example where we take an int and return an int, and it's called next number. And notice next number uses ints random, and it chooses a number between 1 and the number that you feed in. And it gives us a random number back. And so upper is the parameter. If you tell me, give me the next number below 5, it's going to give me a number between 1 and 4. And we return an int. But we use int.random. And every time I call this, I get a different result. And so I call next number below 5. I don't get the same number each time because I'm dependent on this int.random. So what we want to use for our model for pure are mathematical functions. You understood functions in mathematics when you were very young. Of course, it's my bias, but I want to say you loved mathematics. And you learned about the domain and the range. And the domain was the set of all values that you could feed into the function f, and the range was the set of all values that you could get out. So you could think of f as being some map from the domain to the range. But there were some rules. For every x in the domain, you had to get the same y out. You couldn't put in 5 and get 8 one day and 7 the next day. For every x in the domain, there is a unique y in the range such that f of x equals y. And this was our definition of function. When you were older, you might have written the definition of function like this. It was sort of the way of working the word monad into a conversation when you were 12, 13 years old. F maps from D to R, such that for every x in D, there's a unique y in R, such that f of x equals y. It's the definition of function written so that people hate us. So that's a pure function. Is there a notion of pure methods? We don't tend to call them that, but we do have methods inside of our structs that I would like to consider as being pure. For example, look at action. Action is one of those methods that doesn't take anything and doesn't return anything. In fact, if you look inside of it, it is setting values that seem to be outside of the function, and yet the function is really a method. Action is a member of content view, and so our text is disabled and color. They are all members of the same struct. And so the way we picture a method as being different from a function is a method has self as one of the invisible parameters that are passed to it. So it has access to all of the member values. In this case, text is disabled and color, and it can change those values almost in the way that it was returning an instance of self with those values changed. And that's true whether we use state so that the actual storage is being done outside of content view or not. We saw earlier we can store functions and properties, we can pass functions as parameters. We're skipping over the fact that we can return functions from functions. And now we've talked about avoiding side effects, making these pure functions. Unfortunately, there's no way to enforce that your functions are pure. In fact, you often can't even detect this, so it's very easy to make a mistake and involve side effects without realizing it. We've talked about SwiftUI, but the other big release last year was Combine. So here's another demo. Here's a rock, paper, scissors app. You can select rock, paper, scissors using the picker, and then you press your go button to choose one. And now you play the game. Your choice is the bottom choice, And the top choice is from the machine, and then it evaluates who wins. So in this case, we chose scissors, the machine chose rock, we lose. And in this case, we still chose scissors, the machine chose paper, we win. What a fun game. What a great demo. Let's look at what a pipeline might look like in Combine. We start at the left side with a publisher of ints. Now, we often have to worry about whether it fails or not, and if it fails, what's the error that it throws. We're just going to focus on if it's successful and it never fails. And so we're starting with this picker that issues a 0, a 1, or a 2. So it is a publisher of an int. And on the right side, we want to subscribe to a hand position, a rock, paper, scissors, and assign that to a value. And so I've got a publisher on the left side, and I sync that into a subscriber on the right side, but the types don't match up. So in between the publisher of an int and the subscriber that wants a hand position, we need to convert these, and we use a map to do that. And the map can use that function that we had there before that turned a 0 into a rock, a 1 into a scissors, and a 2 into a paper. And now that map, which we call an operator, has converted that publisher of ints to a publisher of hand positions. And now we're in good shape because the subscriber is a subscriber of hand positions. And so now we've got this flow that seems to work across. So you know when you're working with the GUI that you have to make sure you push back to the main thread before you want to display something. And so there's an operator called receive, which allows us to take this publisher of a hand position and just move it to the main thread. So that operator doesn't change that it's a publisher of a hand position. All that operator does is it moves it from possibly a background thread to definitely being on the main run loop. In addition, just the way I've implemented this, I'm setting a value before I'm ready for this whole pipeline to work, before I've hit the go button, just to get things going in the first place. And so I need to drop the first value. Combine gives me an operator that allows me to do that. I can drop the first value, and drop first converts my publisher of an int into another publisher of an int. Map then converts that to a publisher of a hand position. Receive pushes that publisher of a hand position onto the main thread, and then sync allows my subscriber to consume that hand position and assign it to a value. This is what a chain looks like, where the publisher is at first, it starts with nothing and it starts emitting values. The subscriber does nothing with these values that goes on down the chain. It consumes. It's a sink for anything that comes to it. And in between, I've got these operators. And these operators you need to think of as being these pure functions. They take something from upstream and they transform it some way to something that they pass on downstream. Now, this might remind you of something that you've worked with for years with Swift. And that is, say you're processing arrays. I have an array of ints instead of a publisher of ints, and it's got 0, 1, or 2 in it. Instead of dropping the first, we've got the remove first method. Remove first will take the first element of the array and get rid of it. And now I have an array of ints with 1 and 2 in it. And I want to convert from an array of ints to an array of hand positions. And so that's map. Map allows me to do that. And so I end up with an array containing scissors and paper. So let's finish with a few card tricks as we look at some more examples of higher order functions. And for me, a deck is just an array of cards. It's array generic in cards, and a card consists of a rank and a suit. Our higher order functions must accept other functions. And so, for instance, filter, you just have to tell me what the condition is. What is the condition on an element that says it stays in my array? That's just a function from the element of the array to bool. A true means I keep it, a false means I don't. So if I start with a fresh deck that's ace through king of spades, hearts, clubs, and diamonds, I'm going to filter that fresh deck. And my condition for filtering says, you give me a card, and I'm going to filter it. I need some condition on card. I'll keep it if the card's rank is ace. And that gives me the 4 aces in order. We can easily move this to an application that allows us to set the low rank on top and the high rank on the bottom. So here are the cards between ranks 6 and 7, and you can see the 6 and 7 of each suit. Another higher order function is sorted. Sorted takes 2 elements and gives us a bool to say, are they in the correct order or not? So we pass a function in that says, what's the order we expect any 2 elements to be in? Suppose this is your hand. Now, depending on the game you're playing, you might want to order it different ways. For instance, Here's how we could do it in order from low to high by comparing ranks. You'll notice that the cards, irrespective of suit, are arranged from low card to high card. Or instead, you might be playing a game where the suit that you play matters. They are in order by suit, but if you look at the spades, those spades are not in increasing order. And there's a good chance if you play cards that depending on the game you're playing, you first organize them by suit, and then within each suit, you'd go low to high. So how do we do that? We sort, and then we sort again. The first sorted returns a new array that has been sorted, and so we take that array of cards and we sort that. So first we sort the cards by comparing their ranks, and then we sort them by comparing their suits. And now you'll notice that the spades are in the correct order. A well-known higher order function that we've talked about in the context of combine is map. Map allows us to convert one sort of element to another element. So for example, I've got some ints. Here are 5 ints, 1, -49, 38, 125, and 24. And I've got a deck of 52 cards. I'm going to just take that number, basically take its absolute value, mod it by 52, and pick the corresponding card from the deck. And so I'm going to take the ints, and I'm going to choose the card in the fresh deck corresponding to that int, and I get that hand of cards. So map took an array of ints and converted it to an array of cards. I can manipulate cards as well. Let's take a function that takes any card and raises its rank by 1. And if I have a king, it'll wrap around to an ace. So the 2 of spades should become the 3 of spades and so on. So let's take a look at that. I further map by incrementing the rank, and you can see that each rank increased by 1 and the king wrapped around to an ace. So you've no doubt heard about flat map as well. We're going to end with just a small example of where we might use flat map. Now flat map, instead of taking an element to an output, the transform takes an element to an array of output. So we're going to have to flatten the results. So as an example of a function like that, suppose that we start with the 2 of spades. And here's a method that creates 3 in a row from the 2 of spades. So you give me the 2 of spades, I give you back the 2, the 3, and the 4 of spades. And the idea is that if instead you give me my hand, this 2 of spades, jack of hearts, king of clubs, 9 of diamonds, queen of diamonds, if I map that using the 3 in the row, I should get a run of 3 cards for each one of these cards. I should get a hand of hands. And indeed, when I map using 3 in a row, you can see that I have a hand of 5 subhands. Now, I don't want an array of arrays. I don't want a hand of hands. What I want is a single array. If you were dealt this, you would then try to organize them nicely in your hand. And so instead of map, that's what flat map does for you. It flattens this array of arrays into a single array. So instead of using map, we change that to flat map, and now we get a single array of cards. And that's a quick look at how we use functions and how we're going to use them more as we move to SwiftUI and combine. There's map and flat map and filter and combine and just so much more. You'll favor value types over reference types. You'll continue to favor let over var. You'll limit access and visibility of vars. You've realized by now that functions aren't that special. They're first-class objects. You'll use them just as you use strings or ints. And even though there's nothing to keep you from not doing so, you're going to favor pure functions. In addition, you'll write your own higher order function, and you'll leverage the higher order functions that Swift provides you in the Swift standard library. And that's why we need to learn this stuff. Thank you.